Hi guys! This video is the first part of a two-part lecture on the topic related rates. If you have not yet watched the video about rates of change, I highly suggest that you watch that first. Now without further ado, let's begin. In the last lecture, we learned that if I have a variable, say x, and it is dependent on another variable, say t, we can talk about the rate of change of x with respect to t by getting dx over dt. Now suppose I have another variable, say y, and this is dependent on our variable x. It is interesting to note that because of the dependency of the variable y with respect to x, the rate of change of y with respect to t is also dependent on the rate of change of x with respect to t, thus giving us not only a relationship of variables, but now a relationship of two rates, dy over dt and dx over dt. Now, our main concern for today will be talking about what will happen when we have relationships of rates like this. We call this problems on related rates, and that is a problem involving relationships of rates where one variable, in this case y, is dependent on one or more variables, in this case x and t. Now, before we proceed to our next problem, we will be first having a recall that we have discussed last time, and that is, if my dx over dt is positive for every positive time t, then we say that x increases through time, and that is, when time increases, my x value will also increase. In case that it is negative, then we say that x decreases through time, and when it is 0, we say that x remains constant. This will be important later on when we analyze the idea of increasing and decreasing to the sign of our rates. Now let us go to the suggested steps in solving related rates. Now you will see here that this is a very long list, and to aid us in understanding this, I will be flashing an abbreviated version of this on the left side of the screen. I also included there the concept of being positive being increasing, negative being decreasing, and 0 being constant. Now let us proceed to our first problem. A ladder 10 meters long is leaning against the wall. If the bottom of the ladder is being pulled horizontally towards the wall at 2 meters per second, how fast is the top of the ladder moving when the bottom is 6 meters from the wall? Now to understand this well, I will first draw a diagram. Now, it's very important to know that this diagram is what we call a moving diagram, because this should be true for any time greater than 0. Now you will see a related rate problem is a problem where something changes and that will affect and change another variable. In this case, when we draw this, we can draw it in this form where I have a wall, also have the ground, and I have a ladder that is leaning against the wall. You will see that this diagram is true for any time greater than 0. When I say time greater than 0, because I already know that the bottom of the ladder is being pulled at a rate of 2 meters per second. And that is, this part here is moving and thus causing the whole ladder to move as well. But whatever the case, whether I moved it for 1 second or maybe I moved it for 1 hour, it will not change the fact that the ladder will always make a triangle of this form, where the tip of it will always be leaning on the wall, and the bottom part will always be on the ground. The ground will also be perpendicular against the wall, and thus this will always be true for any time greater than 0. Now, it is also important to see that though we have drawn a static drawing here, later on we will be analyzing this as though this is true for all positive time t. And that will be demonstrated through our next step, which is about variables. Now, in my opinion, variables is the most important part of related rates. Now, whenever there is something that moves, in this case, the bottom part of the ladder, you will see there are things that move and there are also things that don't move. Whenever something does not move with respect to time, that means it is constant in this last statement. We will be indicating it by the number where it is constant. In this case, for example, 10. 10 here represents the length of my ladder, and the length of the ladder will still be 10 whether I move the bottom part to the left or to the right, because the ladder is a rigid object. Of course, I will also be assuming that the wall and the ground will also not be moving, and the only thing that moves here will be the ladder. Now, for the things that move, it is important to select variables to represent it. In the third part of the steps, which will be coming later on, you will see that I will be interpreting each rate as a derivative, and thus giving me that note in the second part of the tip if you refer to the left side of the screen. And that is, one good way to select variables is to look at the rates given, rates acquired, and rates required. When you mean your rate given, it means that there is some rate in the problem and I need to have a variable that represents it. In this case, 2 meters per second. Now, 2 meters per second is the movement of this point here going to the left. And I got that that direction because of the statement being pulled horizontally towards the wall. However, I cannot let x, or my variable, to be a point. For one, the point is a couple, so I should have just a single variable. So I will be smart about this, and what I will be doing is I will be letting x to be something else. In this case, I will let x to be a distance. Now, I will explain again later why it is important to let x to be this form, but an important thing to remember is that the variable to be used here is not unique. I can let x to be another part, say from this, the distance from this point to another point here, let's say 100 meters away from the wall, and that will still work. Though it will be more convoluted and tedious, the problem will still be solved using that variable. So I will be letting x to be the distance from this point here until the end point here. You will see that when this point here moves to the left, there's also some sort of change that happens to x, and that type of relationship is important. Now, we do not have a rate acquired here, but we do have a rate required here, and that is, in the problem, we are being asked how fast is the top of the ladder moving. We see that if I pull this point towards the wall, because the ladder is rigid, this point here will slowly go up. So we need to know how fast that part is. It is wrong to say that because this is moving at a rate of 2 meters per second, that this part here will also move at a rate of 2 meters per second. So what we will be doing is that, just like before, I need to know how fast this point is moving, but since I cannot use the point itself, I will be using another distance, in this case y, so that it will be much better to represent it with. Now let's go to the third part, which is also a very important part of our steps, very much closely related to our variables. Now, the third part states that I need to write down the numerical facts and interpret each rate as a derivative. So that means it is not enough that I have a rate 2 meters per second. I need to write that as a rate, or in this case, as a derivative. Now, remember that when I move this point to the left, what changes is the x. So that means I can say that the rate of change of x with respect to t, notice that the direction of this is parallel to the length of x, so therefore this movement is exactly the rate of x, and that will be given by this quantity. Now, there are a lot of things to state about this. The first one is the number -2. There are two parts there, the sign and the number. The number is obviously the 2 that is given in the problem. The very common mistake here is how to get the sign. That's the reason why we emphasize how the word interpret in this part. We need to interpret whether this is a positive or negative, and we got that by the note on the left-hand side. To know whether you are positive, negative, or 0, you need to know what happens to our variable. In this case, variable x. When this point moves to the left, you will see that the length of x will slowly decrease, and thus becoming negative. You will see that it is not because the point is going to the left that we have a negative, but rather because of the decreasing. So in the direction here does not matter much. For one, the orientation of the drawing can be different from what is given here. For example, what I've stated before, if I made the ladder lean in this way and the ground is in this form, when the point will go to the right, I will go towards the wall, then it will slowly go to the right, but though it is going to the right, it is still a decreasing value, so it will still be negative. So whenever you have a problem of this form, it's very important to look at this statements here, like being pulled horizontally towards, so that we will know the sign here. Another one is that the meters per second here are exactly the ratio between the unit of x and the unit of t, and that is the unit for time is seconds and the unit for x is meters. And that's the reason why instead of letting x to be a point, we let x to be a length. So later on, when we see a rate, you will know that the variable that you are looking for will be exactly the variable on this upper ratio on the numerator. In this case, since this is meters, then the x should be some sort of length. Now, that is for the given. Now, the next one is I need to identify what is being asked. In this case, how fast is the top of the ladder moving when the bottom is 6 meters? Now, since I need to know what happens at this point, that's almost the same as saying what happens at y. So I will just look for dy over dt. But this is not enough, because what we need is not dy over dt, but rather dy over dt evaluated at x equal to 6. Now, x equal to 6 is what we call an instance, because as you know, when x is equal to 6, that's a constant value. In our drawing, the length x is constantly changing, but what we want to find out is how fast this point is moving at the instant when x is equal to 6. At this moment, it is very important to note that one of the most common mistakes in related rates is plugging 6 in our diagram, because whenever we have numbers in our problems, we have the propensity to place everything in the problem in our diagram, but that is wrong. In the first step, we stated that the diagram should be true for any positive time t. That means the moment I put a 6 here and then I have a 10 here, then that will force y to be an 8, and that will be a rigid problem already and not something that is true for any time greater than 0. The 6 here will be used at the end. So therefore, the most important part here is not plugging every single number in the problem in our diagram, but rather knowing how the diagram moves, what changes, and everything that is not needed should be put aside first until it is being asked for. In this case, the 6 will be used much later on. Now, this is what we want, the dy over dt. It also states that the dy over dt is not constant, unlike unlike the dx over dt that will always be moving at a rate of negative 2 meters per second, you will find out later on that the dy over dt will have a different value for each instant x equal to 6, x equal to 10, and so on, x equal to not 10, 8, and so on and so forth. Okay, so now let's go to our next step. Now, the first four steps are the hardest part of related rates. The moment you have overcome them, it's much easier now. The next step will be writing the equation relating the variables. Now, this should also be true for any time t. So, at this moment, we are still not studying the instance, but rather still going through to our diagram. In this case, the relationship of x, y, and 10 will always be a Pythagorean relationship, and that is x squared plus y squared equal to 100. Now, this is where it becomes fun, and that is we are now going to be relating the rates. And we do that by implicit differentiation. What I will be doing is that I will implicitly differentiate our equation, x squared plus y squared equal to 100, and that will give me a 2x. And since I will be differentiating this with respect to t, I will now multiply this by the derivative of x with respect to t, and that's a dx over dt. I'll add this to the derivative of y squared, which is just a 2y. And since we are differentiating it still with respect to t, you'll have a dy over dt. And of course, the derivative of 100 is just 0 since it is constant with respect to t. You will see in this relation we have not only x and y, but also the rates dx over dt and dy over dt. And since it is dy over dt that we want, we will now have this quantity here. Now we are already nearing our end. We are on our 7th step, and that is we will substitute in the equation obtained all the values that are valid at a particular time of interest. I emphasize here the statement particular time of interest. This is our instance. So this is now the time that we will be using the x equal to 6. And that is, when x is equal to 6, what will happen is that the diagram will now become a rigid quantity, and not only do I know what x is, I also know what y is. By solving for it, y will become positive 8, and since y is a positive number. And thus, dy over dt at x equal to 6 will be equal to this quantity, negative x over y, where x is 6, y in this case is 8, and dx over dt is negative 2, and we arrive at the answer 3/2. Now, at this moment, we are almost done. We go to our last step. It is also one of the steps that a lot of students forget. But I emphasize how important this is because though 3/2 as a number is great, we need to know what it represents. For example, 3/2 is a rate. And since 3/2 is a positive number, we know that it is the y will be increasing. If you go back to the drawing before, you will see that y increasing means that the tip of the ladder is going upward. And thus, I write that down that the top of the ladder is sliding up the wall at a rate of 3/2. Now, to get the unit meters per second, I go back to the statement that I have before. Since this is dy over dt, the unit will be the unit of y over the unit of t, and that is meter per second. And this is only true when the bottom of the ladder is 6 meters from the wall. See that if I change x equal to 6, the ratio x over y will also be different, and thus it will not have an answer of 3/2 anymore. And that is our related rate problem. Now, honestly, this is a very, very long solution, but after doing a lot of other examples, you will get the hang of it and it will become much easier. Now let's have another example to demonstrate related rates. An automobile is traveling at a rate of 20 feet per second, is approaching an intersection. When the automobile is 100 feet from the intersection, a truck traveling at a rate of 40 feet crosses the intersection. The automobile and the truck are on roads that are at right angles to each other. How fast are the truck and the automobile separating 2 seconds after the truck leaves the intersection? If I were to describe this example, this is an example that really tempts a student to just write every single numerical value in your diagram. Now, this is a very dangerous item primarily because of step 1. Because clearly when you try to draw it, what a standard drawing will look like this. You have a truck that is traveling at a rate from an intersection, rate of 40 feet, and cross the intersection, while the automobile is 100 feet from the intersection. Now, this is a good diagram. However, this is a static diagram, primarily because this only happens when time is equal to 0. Clearly, when at time greater than 0, the truck should not be on the intersection anymore. So that means this is not a diagram that will represent any time greater than 0. Actually, it will not represent it at all, only at time equal to 0. So what I will be doing is I will be drawing a proper or a better diagram, in this case, something of this form. Because when the truck leaves the intersection, it will now be far from the intersection and there will be a distance between the truck and the intersection. While the automobile will not be 100 feet away, but it will be somewhat closer to the intersection than before. Now, you will see that we don't have the numbers 100 here, but that will be okay. As I've said before, any detail that we have not yet written down at this moment can be used later on. So we can set them aside and first prioritize our efforts on how to deal with this moving diagram. So we now have this moving diagram here. We now select variables. There are a lot of rates given here. One is 20 feet per second for the automobile. As I've told you before, one good way to find out what your variable is looking at the unit feet per second. Since we have something over dt every time, then the feet will be a unit of length. So I will be letting a length here, and I think a good length variable here will be this x here. Another rate that is given here is the 40 feet per second, and this is for the truck. Since this point is moving to this downwards, then I can let this variable to be y, and that will be my rates given. For the rates required, we need to know how fast the truck and the automobile are separating. And separating is a distance, so I can now let it to be that length z. And thus giving me the 3 variables that we will be using. So I've said before, these are not the choices for these variables are not unique, but this set is one of the easiest sets for this example. Now we're going to be interpreting now each rate. For example, I need dx over dt. Now, rate will always be given by 3 parts, namely the unit, which we will not be writing anymore since it's not needed yet, the number, and the sign. Clearly, dx over dt will be 20 for the numerical value, but for the sign, we go back to how we determine it. When the automobile approaches the intersection, the x increases, decreases, or remains constant. The answer is decreases. So that means dx over dt will be negative 20 feet per second. For dy over dt, that will be, the numerical value will be 40 feet per second. But since the truck is going away the intersection, then that would mean that the y will be increasing, and that will be a positive 40 feet per second. And what we want here is the rate that they're distancing at the time when t is equal to 2. Now, since we are done with this, let's go to relating x, y, and z. Clearly, The relationship of x, y, and z is just Pythagorean, and that is x squared plus y squared equal to z squared. We will now implicitly differentiate this so that I will obtain the dx over dt, dy over dt, and dz over dt. And I'll have 2x times the derivative of x with respect to t, which is dx over dt, plus 2y dy over dt, and plus 2z dz over dt. Remember that failing to write the dx over dt, dy over dt, and dz over dt will mean that all that we have been doing will be useless. Remember that the most important part here is to relate the rates. So to implicitly differentiate it properly is very, very important. Of course, we need to find dz over dt, and thus, by solving for it, I will just have 1 over z times x dx over dt plus y dy over dt. Now we are ready to substitute the things that are needed. Unlike in the first problem where we are given an x, it's very weird that we are given t. Now, we don't have a relationship between t and x, y, and z at the moment. But if you remember in our problem, which I will be flashing the screen, there are numbers there that we have not yet used. For example, the 100 feet from the intersection. Since I need to know the values of x, y, and z, which are values of lengths, time equal to 2 is a value for time. To get the x, I need to remember that time 0, you are 100 feet away from the intersection. So that means when you move away from it, the remaining value x will just be 100 minus whatever that you have traveled. Since I already know that the rate of my automobile is 20, that will be 20 times 2, and that will be 40. This will give me a total of 60. For the y, since you started at time 0, you started at the intersection, after 2 seconds, you have traveled a rate of 40, rate times time, so that will be a distance of 80. And of course, to get the z, I will just use the relationship, Pythagorean relationship, and that will give me a value of 100. And thus, by plugging everything, 60, 80, 100, as well as negative 20 and 40 on my dx over dt and dy over dt, I will have a 1 over 100 times 60 times negative 20, 80 times 40, and that will give me a 20. And thus, as a conclusion, we say that because 20 is positive, then the distance is increasing. You can also say that the truck and the automobile are separating after 2 seconds at a rate of 20 feet per second. And we got the feet per second here because the prevailing units that we are using here is feet and second. Now, I hope to see you in our next video. In that video, we are going to be doing our last 2 examples. See you!